be here today and talk to you about black holes and take you basically to a journey to find and discover the very first black holes in the early universe. But as with many stories, we basically start here in Cambridge, and this is from a few years ago, over 200 years ago, when actually Newton came up with the idea of gravity, and that basically the things that make things like the apple and that we stay on the Earth, that force that we are attracted to the Earth is basically the same as the force that keeps the planet and the moon and so on orbiting in space. So he came up with this universal force of gravity, as kind of indicated there, that when you have two masses, yes, you have to. Okay, you have two masses and they are attracted by the force of gravity. And it took then only a few years that actually another gentleman here in Cambridge, John Mitchell, came up with the idea that maybe if the mass is large enough that you can bend not just parts of things when you throw them, right? For example, I take an apple or something and I throw it away. It has a curved path. If you would make the mass large enough that even if I would take my laser and shoot light, basically the fastest thing I can shoot into space, it will still be bent. Okay, and this is basically what he kind of wrote already to Cavendish, in 1784, that if you have something that is dense enough, we would have basically that even light would be bent and nothing would be able to escape the surface of this object. And so there basically the idea of a black hole was born, that you have something that is very compact, very massive, and that even light is not able to escape it. This was basically the idea of a black hole that was already born many, many years ago. That idea basically, relied on the fundamental idea that light is a particle, right? That it has basically a very, very small mass and that is still being basically, following these curved paths because it has a small mass. However, if you go, a few years later, Einstein said well, actually, everything is wrong. First of all, light is probably a wave, but it can also be a particle. But more importantly, gravity is not a force. So he basically come up with the idea that gravity is actually the space-time curvature. So the idea now is that, bodies like, the Earth and the Sun, they attract each other because they bend the space and the time around them. And so you keep, the Earth, for example, on the orbit around the Sun because the curve, the Sun curves the space and there is basically a nice movement basically falling along this trajectory. And so Einstein wrote this very beautiful and kind of simple equation as it kind of appears right on these slides, where basically we say that matter tells space how to curve and space tells then how, matter how to move. Okay, so this was this idea that space and time are linked, but also this is then relating to the idea of how things move and the force of gravity, which then again was basically not a force anymore. Now, when Einstein wrote this in 1915, he basically, immediately saw that, this is actually quite a complicated equation. It looks kind of simple on this side. You have basically here something that tells you basically how much matter you have. And on the left, you have the space-time geometry, okay, like the metric. And it's complicated because you have all these, mu's and nu's, which basically mean that you have many different indices. And this is basically a very complicated equation. Einstein was like, well, probably we never find a solution to this, because it's highly nonlinear. Basically, you have to imagine that you have to solve for both things. You have to solve for the matter distribution that is attracted by itself, right, and redistributes itself. And at the same time, you need to solve for the space-time. And these things are basically interlinked. So how do you solve this system? However, only a year later, Karl Schwarzschild, at that time fighting in the First World War, he came up with a solution to this equation. Okay? And the solution is written here. This is basically a solution that describes a point source. So think, for example, a star, or in this case also a black hole, and it explains basically how the star or the black hole is curving the space-time. Okay, and he showed that this is a solution to the equation that Einstein wrote down. Okay, this was only a year later, and Einstein was like, oh, great surprise. We have already solved, at least, one simple system where we have basically a point source and describe how the space-time is curved around it. And when you look at this solution, basically, the idea is that, when you look at a very, very massive system that is very compact, again, a black hole, the idea is that you have the space-time curvature is so strong that you have a singularity at the very center. This is basically where curvature goes to infinity, okay, where it's basically not defined anymore. And then you have a region around this singularity, which is referred to as the event horizon. And this is exactly the region where basically the tracks of the photons, of the light, is so strongly curved that not even light can escape. So if you are basically sitting here, right, outside of the event horizon, you're able to shoot light and it's still able to escape. But once you're inside the event horizon and you try to shoot the laser out, the curvature is so strong that it will always be bent basically back to the singularity. And it's basically so difficult that you cannot really move outward anymore with anything because light is the fastest thing that we have, right? The only thing that is, there's nothing else that is faster. So even you can try, you cannot really move outward anymore, you can only move inward. And you can show that basically it's the same idea that we can only move forward in time when we are outside of the event horizon, right? We can only move forward in time and not backwards in time. When you are inside the event horizon, you cannot even move, outside anymore. You can only move radially inwards into the black hole. So once you're inside the event horizon, you have no chance to escape. So this was the first exact solution, and again, it's still used today to describe, black holes. And so you might wonder now more astrophysically, because this is all the math, right? Like, how do we actually form a black hole? And this is for a very long time not very clear. And what I show you here is basically, how different stars evolve as a function of their mass and time. So imagine that, you form, a star that is similar to the sun, right? And you would be on this track here. And you see that basically the sun, after about 10 billion years, blows up to a red giant. This is, basically expanding its outer layer out to about the orbit of Venus. So it gets quite much larger. And we will not be very happy at that time. But again, it's 5 billion years in the future. So don't worry too much about this at the moment. And then what happens is that basically the outer envelope is basically being pushed away. And what happens is you have a planetary nebula. This is very beautiful to observe. And then you also have in the very center a white dwarf. Okay, and a white dwarf is basically like a star, but it's not anymore fueled by nuclear fusion, right? Like, because the sun, the stars like the sun, what they do is they, take hydrogen and build helium, right? And in this fusion process, you produce a lot of energy, according to Einstein, E mc squared. Right? But, this basically is not happening anymore in a white dwarf, and that's why it's much more compact. And the pressure support, why doesn't this collapse to a black hole, is because you have a pressure support from electrons. Okay, so you basically have a pressure support different from normal stars. And it can go up the mass. So if you form very, very massive stars, okay, you can see that, they will evolve into basically supergiants. And when they then end their lives, once they have used up all their fuel, all the hydrogen burned into helium and then into oxygen and up to iron, once you end up with an iron core, you cannot anymore make fusion efficient. And what happens then is basically the star will collapse and will form a black hole. Okay, and again, you can see that basically the black holes that we would expect from this kind of scenario are probably a few solar masses. So, kind of comparable to, a star like the sun, but compressed into about the radius of about 3 kilometers. Okay, so very, very compact. And this is the idea of a black hole. And you can see that if you go even to more massive systems, they will just explode and not even form a black hole. So this is the main formation channel as we thought that, black holes, form, basically through the evolution of stars, right? You form stars, they will die, and when they die, you form remnants, and some of these remnants are massive enough to form black holes. And so you might wonder what happens then if you fall into a black hole, right? And this leads to basically the idea of, well, okay, we form these small black holes, how can we make them bigger? How can we grow them to be more massive? And so what really happens, and this is a cartoon that probably a lot of people have already seen in some form. Again, going back, what happens is that basically the closer you get to the black hole, the more is the space-time curved, right? And this means that you're getting more and more stretched. And so what happens is two effects, as you see here. First of all, you get kind of like spaghettified, right? You get elongated in one direction. And the other thing is that time will basically slow down. You will just fall in through the event horizon and into the singularity. But an observer from the outside will basically see you being more and more stretched. And the signal that you're sending out, basically, when they look at you, they will see you basically sitting there at the event horizon, basically for nearly eternity. Okay, so these are special and, general relativistic effects that are, a bit more complicated, I would say, to explain. So how do we grow black holes? Again, there are actually many different mechanisms. Of course, as I said, you can actually accrete material, right? And I show this kind of here on the left. So the idea is that, obviously black holes are kind of boring, but then once you bring gas, so for example, hydrogen gas or other, also, gas that is more enriched, basically towards a black hole, what happens is that it circularizes and it starts having this so-called accretion disk. Okay, then an accretion disk basically forms around black holes, and the idea is that some part of the matter, in particular the closer one, will basically be quite hot, but some of it will be absorbed by the black hole. And so this is a way that you can basically grow black holes. But there are also other more exotic events, because this is something that we have, as I will show you, observed already several times. These things are more difficult to track. Again, we think that actually black holes can swallow other black holes. These are so-called black hole mergers. These are things that I will mention when we talk about gravitational waves. But we also can have tidal disruption events. And these are basically just stars that get too close to the black holes and get shredded. Okay? And you basically see this, what happens here. Really, stars like the sun would basically be shredded apart, and then you form again an accretion disk basically at the very, very end. So these are different ways of how we think we can grow black holes through cosmic time. Can we observe this? And indeed, so I mean, there was actually Cygnus X1. This was one of the famous X-ray sources. So this emitted a lot of light in the X-rays, very high energy photons. And there was actually an interesting bet between Kip Thorne and Stephen Hawking at the time in 1975, where basically Kip Thorne was like, this is for sure a black hole. This must be a black hole, whereas Hawking at that time, kind of betting that it was not a black hole, but kind of intrinsically, I think, hoping that it is a black hole, because this was basically then the first object where the majority of the people agreed that this is probably a black hole. And indeed, Hawking conceded the bet in 1990. And this is, again, a very specific object that's kind of indicated in this, cartoon. What happens there is that many stars are actually not born in isolation. So many stars are born actually in pairs. And what can happen is that these pairs, of course, don't have exactly the same mass. So, one star might evolve quicker than the other, will turn into a black hole. The other star will start its shine phase, so then expands. And then at some point, probably the gravitational influence of the black hole is so strong that there is material that can be transported from the neighbor star, from the donor star, to this black hole. Okay, and when this happens, again, you form an accretion disk, and this accretion disk is basically very hot, right? It has, basically, a few 10,000, degrees Celsius in the outskirts, and then 1,000,000 degrees Celsius in the very, very central region. And again, this is so hot that it emits a lot of light in the X-rays, and so very high energy photons, and can be easily observed. This should be black hole. Okay, so when we think about accretion disks in more general terms, what you see basically is that we have this gas swirling around the black hole. We can also have jets, and we have basically other gas pockets around it. And this gas, you have to imagine, is moving very, very quickly, right? We're talking here of thousands of kilometers per second, right? It's moving very, very fast. And why is this important? Well, here we have cartoons, right? Because we have a hard time to take images of this. But what we can do is we can take spectra. So we can we can measure the light, and we can, split it up as a function of wavelength. And when we do this, right, we can get spectra like those. Okay, so this shows basically the amount of light you have as a function of wavelength. And you can see that some of these lines, like the H alpha emission line or H beta, are very broad. Okay, so they are broadened, and this is basically because this gas is moving very quickly. Some part of the gas moves towards you, some part of the gas moves away from you. You have this normal Doppler shift effect, and this leads to the broadening of these emission lines. And so even though we cannot see and spatially resolve the accretion disk, we can spectrally, in the spectra, see them very active. So how can we know more about black holes, right? And this is something that is actually nice to illustrate on our own, the Milky Way galaxy. So this is an image of Andromeda, the neighbor galaxy, but it's a very similar galaxy to our own Milky Way galaxy. So let's assume it's the Milky Way. So where is the sun? The sun is a random star in the very outskirts. Okay. There are, more than 10 billion stars, right? So there are a lot of stars, and the sun is just a random one sitting in the outskirts of this galaxy, basically moving around, the Milky Way center. Okay. And you can, try to estimate this and measure, and you come back and tell me that basically takes about 230 million years for the sun to complete once its orbit. Okay. And so you might say, wow, the sun is moving very, very slow, huh? And the answer is actually not that slow. The sun moves with about 143 miles per second, okay? So the sun is actually moving very, very rapidly, right? And we, the Earth, move around the sun and, and so on and so on. But again, the sun is moving very rapidly. And what this basically shows is that the Milky Way galaxy is just very, very large. If I would send light from the center, and again, imagine that light travels with about 300 million kilometers per second. It takes light to travel from the center to the sun about 25,000 light years. Okay, so about 25,000 years. So if we are looking at the center of the Milky Way, of our own galaxy, we look actually 25,000 years into the past. Okay, so let's look at that. Okay, so this is basically showing you the very, very central region of the Milky Way galaxy, and we basically can see really individual stars there, right? And even better, for the last 20 years, we have been observing those stars, and their positions, and we are able to basically track their orbits. Okay, so we're just looking at the orbits of those stars, and this led to the Nobel Prize a few years ago. You see here, this is from the year 2000, and we are basically zooming in onto the very central region of the Milky Way, and you can see basically how the stars orbit. And S2, one of the most popular stars, is indicated with this red curve, and you can basically see how it 14, 15, 16, how it moved past this red cross here. And so from these orbits, okay, even just Newtonian mechanics, you can estimate basically how much mass, okay, how much matter do you have in this region where there's basically nothing, right? We don't see anything there. So what's there? And the answer is that if you estimate how much mass there is at least 1 million solar mass object there. Okay, 1 million solar masses. And this is just highlighted in this cartoon. Basically, again, this is the star S2 that moved past this black hole. And again, it moved with more than 25 million kilometers per hour, right? So this star was moving very, very rapidly. That's why we could see it basically moving, on a daily basis. And the only solution of how you can put so much mass and matter into this region is basically via a supermassive black hole. Okay, and the supermassive black hole of the Milky Way is about 4 million solar masses. And now you should wonder, right? So I told you all about, we form black holes and there are a few solar masses, right? They are remnants of stars. And now I'm telling you that we have these black holes in the centers of galaxies, like the Milky Way galaxy, of million solar masses. So there is a bit of a discrepancy, right? So how do we go from a black hole of like a few solar masses to one that is 1 million solar masses? So that's a good question. Now, this is not the only black hole that we found. Okay, there is actually today the overall agreement that every galaxy has a supermassive black hole, and the one of the Milky Way is actually a lower mass black hole. Okay, even though it's 1 million solar masses, it's kind of a lower mass. So how can we go about this? And here I want to mention the Event Horizon Telescope, where basically what we want to do is we need to understand basically this accretion disk and the photons, the light, traveling around black holes. And in order to basically resolve this, to see this sharp in an image, what we need to do is we need to resolve basically a tennis ball on moon. Okay, that's the challenge, right? So you take this thing, you put it on the moon, and you want to take a picture of it. Okay, that's the challenge. So what we basically mean, and you will learn more about this when you talk about telescopes afterwards, is you want to build a very, very large telescope, right? You want to basically have, as large of a mirror as possible. So what's the largest possible telescope we can build? Well, probably the one that is the size of the Earth. And you can do this with interferometry and in the radio. So this is the idea of the Event Horizon Telescope, where you basically couple different radio telescopes, around the globe together, and basically generate, or then put together in the computer, synthesize basically the wavelengths to basically then generate, an image from a telescope that has the size of the Earth. And the data volume is so large that you cannot really send it anymore by internet. You have to go to the South Pole Telescope, actually, and get the hard drives and bring them back to Europe to do the synthesization. And so what has been imaged is basically this. And the way that we then interpret this is basically with this idea that you have light, okay, so light traveling basically around the black hole, okay, leading to this photon ring that you're observing here. And you can then estimate very well what is actually the mass enclosed. And again, the galaxy M87, so one of the larger elliptical galaxies in our neighborhood, has a black hole mass of at least a billion solar masses. So again, this is 1,000 times more than the one from the Milky Way. So how else can we find black holes? Again, you might say, well, okay, we have to understand really how they grow, and I agree. So we have to go and look for, mergers, for example. So the idea that when you have two black holes merging together, what happens is that they, in spiral, okay, they will lose angular momentum, okay, and they will move around always faster and faster. And so this energy that they basically lose, right, this angular momentum needs to be transported away, and this energy is being radiated away with so-called gravitational waves. So what does this mean? This means that you have basically these two black holes. Imagine that they are swirling around each other, and this leads to perturbations in the space-time, okay? And these waves in the space-time, they travel with the speed of light, and basically today we are trying to detect them. And so how do we do that? We do this with a basic, Michelson interferometer, which is kind of indicated here, where you send a laser, okay, and you first, have the laser coming out here. You do a beam split, so one part of the laser goes here, the other laser goes here, and they can move forth and back a few times, come back together, and you look basically whether, they have traveled the same distance or whether they have a slight offset, okay. And when they have a slight offset, this means that, after building these arms exactly the same length, that this offset has been introduced by basically changing the space-time a bit. Okay, so this is the idea of such a detector, which is called in this case LIGO and Virgo. So what is kind of the accuracy that you need? Well, you need to go basically below the scale of atoms. So this is the accuracy. This is basically the amount of change in the space-time that I expect. Okay, less than an atom. Okay, so that's why it took quite a bit of time to build this and make sure that we understand this. And the main thing is, as you see here, is actually that we have two of them, and actually three now. Okay, and you build them at different places. Okay, you build them once, in kind of the Washington area, Washington State in the U.S., and the other one more towards Alabama. And the idea there is that they have slightly different noise sources, because even though you are hundreds of miles away from the coast, you can still feel and hear basically the crashing of the ocean, okay, of the waves. And so this is like basically the accuracy that you need. And what has been observed in, nearly 10 years ago now, or 9 years ago, is basically, this is the signal. So these black holes merged far, far away. They released basically the gravitational wave. And you can see basically how this wave basically kind of, was then, was coming in here. And you can see this is the time. So this is a very short, time interval. So only less than a second. And here this is showing you frequency, basically. What this means is that basically what's the frequency of this wave? And again, because they spiral in, the frequency increases. Okay, so this, if you would listen to it, sounds like, okay, this is the, idea of this, mass, two black holes that are circling around each other. And so this is for sure a channel that is important. And nowadays we have observed actually already hundreds of those events. Okay, so this is mapping out basically, each of these tracks shows you which kind of black holes merge to form what kind of black hole. Okay, so you can, for example, take these two, so there are two black holes. Okay, one was, about 7 solar masses, right? The other one was about 10 solar masses. And you firm them together and you form something, around 18 solar masses. Okay, so each of these tracks shows you basically all the black holes that merge together. And that looks great, right? So we can see that there are a lot of black holes and they're all merging. And the problem, I guess, is that you see that the most massive black hole that merged is kind of 200 solar masses. So we are still orders of magnitude away from forming supermassive black holes, right? So you might say, well, this is maybe not the right channel. Well, I might tell you that this is maybe we're looking at the wrong frequency. Okay, so basically detectors are too small on the Earth, right? They are just finding small gravitational waves formed basically from small mergers. So what we need is a larger detector. So let's go and build that. Okay, now, sorry, that moved a bit too fast. This is basically shown here. So this shows you basically the time scale, the frequency of these waves, right? And we are talking about ground-based experiments at the moment, and we are finding merging neutron stars and black holes. What we need is to basically go to space to build larger arms, okay? And this will allow us to then start, finding basically more massive, supermassive black holes merging. And this is the idea of LISA. So LISA is basically a mission that, we try to build 3 of those things that basically send lasers among them. And the LISA will basically circle the sun. It's just about 20 degrees offset from the Earth. Okay, so it will basically move with the Earth around the sun. Okay, this is currently being tried to be funded, and there's still a debate how much NASA is contributing and how much ESA, the Europeans, are contributing. But this is something that is happening and hopefully happening within the next 5 to 10 years. What happened more recently is the James Webb Space Telescope. So I'm telling you a bit more about this and how we learn more about black holes from this. So I could tell you, a whole hour about the James Webb, and I'm not, don't worry. But basically, the James Webb Space Telescope has launched about 3 years ago, right? And it's taking really great images, but also spectra of the very deep space. And I myself, I'm part of the NIRCam science team, so that built basically the NIRCam infrared detector that is on this telescope, and we have been doing a lot of data analysis. And what I show you here is basically some of the very deepest images we have taken. Okay, so this is showing you basically now in a very deep image, not too far away actually from the northern sky today. And what you're zooming in here is on a very specific object called GNC11. Okay, so this is one specific object. Why is this a very interesting object? Because we were able to take a spectrum of this object, and basically what you're seeing here is that you have more and more UV light, and then it kind of breaks, and you can see there's a wide range of different emission lines. Okay, and we can use these emission lines now to learn about what actually powers them. Is it the stars? Is there a black hole? What is really curious about this object is that this object is actually very, very far away. Okay, so this object probes basically the first 500 million years after Big Bang. So what this means is that the light that we receive today traveled to us for more than 13 billion years. Okay, so we're looking really kind of at the very first galaxies in the universe. And now with the James Webb, we are for the first time able to basically understand what's happening in those systems. And when you look and squeeze your eyes, you might see that these lines are indeed a bit broader. Okay, and so this again is actually the direct indication that we think that a lot of the light of this object, because it's very compact, but also from the spectrum, that this object is actually powered by a supermassive black hole. Okay, and so you can go back to this cartoon that I showed you before, right? So what we're basically seeing is, more than 13 billion years back in time, the gas that is moving around a supermassive black hole. And the black hole that has been present there is already, over 1 million solar masses. So that make the problem worse, right? I tried to tell you we have a massive black holes, supermassive black holes in the local universe, but now we have them already formed 500 million years after the Big Bang. Okay, so that makes it just worse, right? Because now I have even less time to grow them. Okay, so how do we solve that? Well, actually finding even more puzzles. And these are systems that were very surprising to us. What we find is basically a lot of red dots, and we just called them, as always astronomers, little red dots because we don't know what they are. They're really just little red dots. And the best models, okay, when we look at their spectra, again, they are very broad, they have very broad emission lines, and they have even self-absorption, which means that actually what we're looking at is probably gas that is moving around the black hole, but somehow you need to have other gas around it. And the idea, basically, that is being pushed around at the moment is that you have this supermassive black hole, you have the accretion disk, but you also have very dense gas around it, something like, a star, okay, that leads to this self-absorption. So we have too many supermassive black holes formed already too early. So you might wonder then, okay, do you even see the galaxy there, right? Because I told you like a lot of this light is actually being, powered by the black hole. And we try to make diagrams a lot in astronomy, so I keep you simple here, but what I show you here is the mass of the black hole, and here is the galaxy mass. We know today that, small galaxies have smaller black holes, bigger galaxies, more massive galaxies have more massive black holes. And you might wonder, okay, is the connections just straight, right? Maybe they grow up together. You form galaxies and black holes at the same time. Actually, a lot of models, when we look at simulations, numerical models, what they predict is actually this path here, that you have first the galaxies growing and then you form black holes in them. And the other scenario is basically that black holes are formed first and then you have the galaxies forming around them. And what JWST clearly indicates now with more and more data in the last 2-3 years is really that we are much more in this channel. Somehow we form black holes very efficiently, and then we form galaxies later on. And so we still don't know why this is the case, okay? So what can be possible scenarios for now forming these supermassive black holes? And these are more ideas, okay? And again, the idea is that you maybe have galaxies forming in these so-called dark matter halos, and you have the gas there. And again, the standard scenario that I kind of highlighted at the beginning is that we form stars, and these stars, they explode and form black holes. And we might have different kinds of stars in the early universe, maybe population 3 stars that are metal poor, and they form very, very massive stars, and therefore very massive black holes. But it's hard to get over 1,000 solar mass black holes, basically. there is the idea that you might have not enough any pressure, so maybe the gas is really just contracting and forming directly a black hole. And in these scenarios, you can indeed actually form directly through a collapse 1 million solar mass black holes. And the other way is through dynamical instability of star clusters, where you basically form stars, but they have somehow an instability and there's a runaway collision and you form black holes, probably of the mass of a few thousand solar masses. And there are even more exotic scenarios, things like primordial black holes that might be a remnant of the inflationary period, but then at the end of the day, in addition not understanding the seeding, we really don't understand how they then also grow, right? Because I told you about the different growth channels, but the question is basically that the seeding mechanisms and the growth channels are very degenerate currently in our data. Okay, just to wrap up. So basically, how do we make progress? I told you about LISA, right? That is very exciting, but even earlier we have the extremely large telescope, again, that we here in Cambridge are very heavily involved in. The idea there is to build a telescope that has, works in the optical and near infrared and has a mirror size of about 40 meters. So again, this will allow us to take very sharp images also of these little red dots. So maybe they're not so little as we think, so we can spatially resolve them, but also then basically making very deep images of the sky to learn more about the formation channels of these supermassive stars and black holes. And so with this, I just want to highlight basically how this thing being built. It's not built so fast, so don't have hopes. But basically, the idea is that you have these segmented mirrors. And this was from 2023, I think. So you see that, the dome is being built. And this was from earlier this year. So this is really heavily under construction. And the hope is that in 2028, I can show you some of the first images of this telescope. So I think this brings me to an end. Thank you very much for listening.
Questions for Sandro? Yes, very keen. First one.
What exactly happens to you? Like, what does it feel like to be sucked into it?
Yeah, so
What's on the other side of it?
Yeah, it's a very good question. So it's actually quite boring. So you will cross the event horizon without any problem. You don't feel that actually. Okay, so you as being you falling in, you will just fall through the event horizon, have a good day, and keep going. Then I'm not exactly sure what happens at the singularity. Okay, there we argue whether there are wormholes or not. Okay, so we don't really know. But for you, not much happens when you fall into the into the event horizon, into the black hole itself. Well, you disappear from the outside. Like when somebody would look at you, they would basically see you being more and more stretched, and basically then slowly approaching the event horizon, and basically never really crossing it. But this is just because the signals that are being sent out, basically have to climb up this this stretched path longer and longer. But for you, you will just pass through. And again, this is the challenge, I think, to understand general relativity and these theories, because different observers have very different perceptions of actually what happens.
Has anything ever fallen into a black hole?
If anything has fallen into a black hole?
Like
Any humans? We don't think so, no. Not to my knowledge, yeah.
Any more? Yes, please.
What's a black hole made of?
That's a good question. So I think that in principle, all the material, that has been sucked up. Okay, so indeed, like when you think about stars, right, what they basically are made up of is at the beginning hydrogen and helium, but at some point, again, the material in the center is mostly iron. And then the question is exactly what happens to this material, but the idea is that you really just bring it all together in a very compact form. Now, there are theories that say, well, we can describe black holes perfectly by just its mass, so how much matter there is. We don't really care what it is made of, because the idea of Einstein and other people is that, there is energy and mass is equivalent. And so it doesn't really matter, matter what the matter is made of, because you can always transport it in energy. And these things are basically equivalent. And so yeah, it's possible that basically a black hole, all the matter that we know, like for example, this thing would just be transformed into being a form of energy.
So many questions. Yes, how are you?
Do you have a favoured theory for how some black holes can get so atomically large, like upwards of 100 billion solar masses in some cases?
Yes. So I always have, favorite theories, I guess. But the key thing, I think, is exactly the question is how do you form these early black holes in the very first instance? And I think there we have some ideas. So again, I think that star formation, the amount, you can form stars quite quickly in the early universe. And I think these runaway, star clusters, you can quite quickly form, black holes of, maybe 1,000, maybe 10,000 solar masses. And again, the universe at the early times is quite dense. So we think that the accretion rate, so like how amount of gas you bring in close to a black hole might be quite high at early times. And so there might be enough time to actually take these, 10,000 solar mass black holes and bring them up to 1 million or more solar masses. So what I would say is that you might have just higher accretion rates onto these systems than what we have previously thought.
Excellent. Let's go over this side. Yes, please.
Are there any theories about how black holes are interacting with the dark energy that's decomposed?
Yeah, there are some ideas, but I don't think any of them are very serious. Yeah, so I don't think that this connection is well established, basically. So I mean, we try to understand what is dark energy, and we don't really know what it is. So I think it's worth exploring different ideas. But at the moment, the idea of black holes being connected to dark energy is basically kind of a very far away idea. Yeah.
Yes, please.
How would we defend against the black hole if one came into or near the solar system?
Yeah, I don't think we have much choice. It's kind of hard to avoid being sucked up if the black hole comes too close. The hope would be that we would discover it early on, but it might move so quickly that we know it when it's too late.
Could we use like a Dyson sphere or something?
Well, if you are able to catch it in the sense of like, move with the speed of the black hole, depending on what kind of black hole it is, you could build something around it. But the idea of having a solar mass black hole basically moving in the Milky Way is not too crazy. The chance that it will collide exactly with us is very, very small, because I kind of told you that the Milky Way galaxy is very, very large. So even though it seems like there are a lot of stars, there's basically a lot of empty space between the stars. So if you would take the Milky Way and shrink it, basically, shrink the stars to the size of my thumb, the distances between the stars and the thumbs would be like between different capitals in Europe. So there's a star in London, size of my thumb, and the next one would be in Paris. And in between, there's basically nothing, a few planets. So the chance that a black hole would come too close to us is actually very, very low.
Okay, let's go to you near the top.
So before a black hole is created, how do you sense the energy that's there before the first one?
Oh, yeah. Can you, a bit louder?
Yeah, just the last part, yes?
Before a black hole is created.
How do you know that? How you know?
Okay, well, so for example, so one way of creating the black holes that I mentioned are these, big explosions, right? And these explosions are actually quite easy to see because they are very, very bright, okay? And so this is one of the main channels, at least, today, how black holes are forming, right? Through these explosions of stars. And, for example, when you go back to the supernova 1987, right? This has been observed, at many different wavelengths. And also now, basically, we can go back and observe it. And so there, basically, we can establish, what is actually the progenitor star, how much, energy was there released in the explosion, and also how much is left over and forms this black hole.
My second question.
Do you mind if someone else gets to ask one? Because I think you've probably only got time for one left. Is that okay? You can come up in the break and ask, I promise. Okay, let's go with you for the last question.
Alright. Is it true that we can accidentally create a black hole at the Large Hadron Collider?
Yeah, so there are these ideas, right? Because what you basically need is a lot of energy, because it is like mass, right? So you need a lot of energy in a very, very small, tiny space. And so in principle, yeah, you could form a black hole, but the theories that predict them forming also predicts that they basically immediately, annihilate. So basically being, evaporate again, okay? And so we don't have to worry that if we generate a black hole, it would suck up everything, basically. So we don't have to worry.
Okay, fantastic. I can't see more hands. Sandra, are you happy to stay around in the break
Sure,
and
yeah.
answer a couple more? Okay, so just